All right, so now we know how to graph sine and cosine, and we know how to transform it. We can graph the sine of 2x, 2 times the sine of x, the sine of x plus 2, and so on. So now it's time to take a look at graphing the other trigonometric functions. So far we've done sine and cosine, so we need to deal with tangent and cotangent, secant and cosecant. Let's take a look at tangent first. The graph of y equals the tangent of x will look something like this. We'll graph this by taking some values from a table. But the first thing to notice is that, or the first thing to remember, is that tangent can be defined as sine divided by cosine. So the tangent of 0 is 0 divided by 1. That's just 0. The tangent of pi over 6 is 1/2 divided by root 3/2. So because the denominators are the same, I can cancel them and I get 1 over the square root of 3. The tangent of pi over 4 is root 2 over 2 over root 2 over 2, and anything divided by itself is 1. The tangent of pi over 3, that should be a 2 there, is root 3 over 2 over 1 over 2. So there, root 3 over 1, or root 3, is my tangent value. And the tangent of pi over 2 is 1 divided by 0. Well, we can't divide by 0, so this is undefined. So now what I have, at least for quadrant 1, is a set of coordinate pairs, the theta value and the tangent value, the theta value and the tangent value, and so on. And because the theta value is my input for each of these, and the value of tangent at that input is my output, I get coordinate points. Let's go ahead and plot these. I'll start by making a graph that goes out to 2 pi. I'll cut that into pi, and then that's pi over 2 and 3 pi over 2. And then that one's pi over 4, and so on. And around the pi over 4s, I get a pi over 6 and a pi over 3. That's how these get divided up. This is a pi over 4 as well, so that gets some extra tick marks. Not every tick mark gets those extra 2, just the pi over 4s. All right, so let's go ahead and plot some of these points. We have 0, 0, pi over 6, comma, 1 over root 3. Well, guess what? I think I'm going to need a calculator here. I need to approximate these so that I can graph them. I'll need to do that there, here, and here as well. So I just grabbed a calculator and figured out what pi over 6 was to 2 decimal places. Again, since I'm graphing and my pen is really much too big to do anything with any real accuracy, that's close enough. So to plot the point pi over 6, 1 over root 3, I'm going to go out to pi over 6, which is here, which is about 0.5, and up 0.58, or almost 0.6. Well, I don't have a scale on here yet. So let's go 1, 2, 3 and see what happens. So I need to go out pi over 6, that's in the x direction, and then up 0.6, so about there. So I'll have a point roughly here. And then for pi over 4, I could have left these values as pi over 6, pi over 4, and pi over 3, it occurs to me. I need these to be numbers that I can find easily on the axis. I've already got my x-axis labeled in terms of pi, in terms of radians. So let's go pi over 4, comma 1. I'm going to go out pi over 4 and up to 1. That means I'm going to have a point here. And then I have a point at pi over 3, comma root 3. Well, that's pi over 3, as it turns out, 1.73. So right about here. All right, so in quadrant 1 anyway, it kind of looks like tangent is doing something like that. Let's take a look at one more here. And in fact, there are two more values I want to look at. One is one between pi over 3 and pi over 2. You won't necessarily need to do this every time. I just want to show you what's going on in between those two values. So I'm going to plot the point 5 pi over 12, comma, whatever its y value is. And I've kind of not given myself enough room here. So let's move things along a little bit. There we go. I don't know how much room I'll need for my decimal either, so I'll give myself some more space. The point 5 pi over 12 on the x-axis is halfway between pi over 4 and pi over 2, which is right here. So in yellow, this is 5 pi over 12. As I mentioned in a previous video, you can actually divide these all up in terms of pi over 12, and then you get nice evenly spaced tick marks. This is 1 pi over 12. This is 2 pi over 12. Here's 3 pi over 12, and that's pi over 4. 3 pi over 12 reduces to pi over 4. 4 pi over 12 reduces to pi over 3. There's 5 pi over 12. That's a new one. Here's 6 pi over 12, which reduces to pi over 6. So if you want nice even tick marks, you can say pi over 12 is the distance between any two tick marks. It's a little bit of a bonus. Most people don't sort of think about the values on the x-axis this way or around the unit circle this way. But if I were to draw the unit circle the way we've been drawing it, there's my 45, there's my 30, there's my 60. So this is pi over 6, pi over 4, pi over 3. Well, these are all multiples of pi over 12, with the first one and the fifth one missing. So now I have 1 pi over 12, 2 pi over 12, 3, 4, 5, 6 pi over 12. And you can continue that all the way around. Kind of fills in those gaps, and it makes it, I think, makes it easier to remember. Anyway, that wasn't my point here. My point was to plot an extra point, 5 pi over 12, whatever its y value is. I'm just going to do that on the calculator. I'm going to take the tangent of 5 pi over 12, and that's going to be the value that goes in there. When I do this on the calculator, I have to make sure that my calculator is in radians before I begin. Otherwise, it'll give me the wrong value. Our graph seems to suggest that it's going to be up here somewhere. But let's see, the calculator tells me that the tangent of 5 pi over 12 is 3.73 to the nearest 2 decimal places. That's 3 3/4 near enough. So my point from this input value is going to be way up here at 3 3/4. See if I can do this. Right about there. My graph does indeed continue up. The question is, how far and in what way? Does it behave like a quadratic or a cubic, or is it asymptotic? And the answer is, it's asymptotic, because at pi over 2, tangent is undefined. And what that means in the real world is that we have an asymptote at pi over 2. So I've actually already overstepped my asymptote here. I should back that up a little bit. I have an asymptote at pi over 2. So my graph of tangent will continue up in an asymptotic fashion. It'll get closer and closer and closer to the line x equals pi over 2, but it'll never touch it. All right, I'm going to erase this work down here so that I can make my chart a little bit bigger. And I need to make it bigger in the horizontal direction, so I'm actually going to move some things around. Unfortunately, yet again, my software won't let me do this unless I do it one step at a time. And when things get, when they get associated with each other in the software, I'm not really entirely sure how that happens, why they get grouped the way they do. Anyway, so now what I want to do is find the sine, cosine, and tangent for values bigger than pi over 2. And I was going to fill this table in before I started recording, but I wanted to show you quickly how I do that using this idea of 5 pi over 12. I have 5 pi over 12 in here, pi over 12 in here. That's 1 pi over 12, 2 pi over 12 is pi over 6, 3 pi over 12, 4 pi over 12, 5 pi over 12 would be in here, 6 pi over 12. The next one would be 7 pi over 12, but we don't usually use that one. Then 8 pi over 12, which reduces to 2 pi over 3. Then 9 pi over 12, which reduces to 3 pi over 4. Then 10 pi over 12, which reduces to 5 pi over 3. Then 11 pi over 12, which usually gets left out. Then 12 pi over 12, which is pi. So in white here, this is quadrant 1. And in the same ways I highlighted my graph when I was graphing the sine function and the cosine function for you, I'll highlight quadrant 1 in this version as well. So highlighted in white, that's quadrant 1. Quadrant 2, I'll highlight in yellow. And that's going to go, let's see if I put another, I'll put a dotted line for now. We'll decide whether it's going to be an asymptote. I kind of missed pi there. Let me back up just a little bit. Make sure I get that in the right spot. Still not great, but it'll do. All right, so here's quadrant 2. And I'm going to apply the same logic as I did for sine and cosine. I know the values for the tangent of 2 pi over 3, 3 pi over 4, 5 pi over 3, and pi because I know the values for the tangent of 0, pi over 6, pi over 4, pi over 3, and pi over 2. Only the question is, are they positive or negative? So as a quick reminder, I'll just put this up here. I highlighted quadrant 1 in white, quadrant 2 I'll do in yellow, quadrant 3 I'll just go ahead and preliminarily color that in green, and quadrant 4 I'll do in pink. We've done quadrant 1, everything's positive in quadrant 1, so notice that all my y values here are positive. In quadrant 2, only the sine and its cousin cosecant, only those are positive. So tangent must necessarily be negative in quadrant 2. So my values for quadrant 2 are going to be the same as the values for tangent for quadrant 1 in reverse and with a different sign. Now, technically, pi over 2 isn't in quadrant 1. It's on the boundary between quadrant 1 and quadrant 2. So that boundary, my pen's not working, there it is. That boundary is really not in quadrant 1 or quadrant 2. Because it's on the boundary, this undefined, this asymptote, is the boundary between these two regions. So I don't repeat this value. I only start repeating with the square root of 3, and then 1, and then 1 over the square root of 3, and then 0. But I do need to go back in and change all their signs. Now, of course, it doesn't matter if 0 has a negative on it because 0 does not have a sign. It's the only number, it's the only real number that's neither positive nor negative. I also know from a previous screen that the values of root 3 and 1 over root 3 can be approximated by, let me get the right pen here, root 3 is about 1.73, now it's negative, and 1 over root 3 is about 0.58, and now that's negative 2. So this time, instead of plotting points like this, 2 pi over 3 comma negative 1.73, I'm not going to write those all out this time. In the case of quadrant 1, I had 0 comma 0, pi over 6 comma 1 over root 3, pi over 4 comma 1, and so on. So I'm just going to do the same thing here. Instead of writing all those points out, I'm going to assume that you can follow that the values that I'm taking, the points that I'm about to plot here, come from the combination of this x value and this y value. So 2 pi over 3, I need a height of about negative 1.73. That's about 1 1/4. Let's see, I don't have any tick marks on here yet, so let's put some in. I'll go to 4 in this case. And then I'm going to go 2 pi over 3, negative 1 3/4. So about there. And then I have 3 pi over 4, which is this tick mark here, is my x value. 3 pi over 4 goes with -1. So 3 pi over 4, -1 is about there. And then 5 pi over 3, -0.6. This one here is 5 pi over 3. This is 3 pi over 3. This is 1 pi over 3. Oh, that should be a 6. My apologies. This should be 5 pi over 6. Let me fix that. So this is 6 pi over 6. This is 1 less than that. That's 5 pi over 6. And so I have the point 5 pi over 6, comma, -0.6. So I'm about there. All right, let's see what's happening at pi. Now, pi is also a boundary. If I look at this diagram, I'm starting at 0. If I go around the circle, there's no circle here, but hopefully you can imagine one. Then I get to pi over 2, which is a boundary between two quadrants. Then I get to pi, which is another boundary between two quadrants. And eventually I'll get to 3 pi over 2, which is another boundary. So pi, 3 pi over 2 are boundaries. So pi also technically should not be highlighted because it's not in any quadrant. Okay. So what is the value of tangent at pi? Well, if I take the same approach as I took for these other values here, and I just write down the number that I found here, but change its sign, then I'm going to have 0. And it turns out that's exactly right. So at pi, my y value is 0. All right, let's extend the chart one more time. And this time I'm going to be in quadrant 3, which I decided earlier was going to be green. So if I add this is my boundary here. This is 3 pi over 2. Put my boundary in, and then I'll highlight it to match. I was never good at coloring books either. All right, and then I have to figure out what my angles are. Well, if I think in pi over 12s, then pi would be 12 pi over 12. So my next angle would be 13 pi over 12, and the first and last ones in each quadrant we tend not to use. 14 pi over 12 is 7 pi over 6. 15 pi over 12 is 5 pi over 4. 16 pi over 12 is 4 pi over 3. 17 pi over 12 is one that we leave out. And 18 pi over 12 is 3 pi over 2. Now, I'm going to rewrite that one because 3 pi over 2 is a boundary. 0 is a boundary between quadrant 4 and quadrant 1. It's 2 pi. If you're coming around this way, you get to 2 pi, and then you start over again at 0. Pi over 2 is a boundary between quadrants 1 and 2. Pi is a boundary between 2 and 3. 3 pi over 2 is a boundary between quadrants 3 and quadrant 4. So I have 3 pi over 2 here as a boundary, so it's not highlighted. These boundaries are not in a quadrant. All right, so now I'm going to take a look at those values again. Here I had 0 up to root 3 and then undefined. That was one of my boundaries. And then I went backwards from root 3 back to 1 over root 3 back to 0. Now I'm going to start over again. 0 is actually the value on the boundary, so I'm not going to repeat that one. I'm going to start repeating here. So I have 1 over root 3, and then 1, and then, let's see, root 3. And then the next one, that next boundary, will be undefined. Now I'm in quadrant 3, which is green. So that means that tangent is positive. So all of these values are going to stay positive this time. And I can plot the points. 7 pi over 6, 1 over root 3. Let's get those decimal approximations again here. We have 0.58, or nearly 0.6 there, and 1.73, or about 1 3/4. So now I can plot the points. 7 pi over 6, that's going to be this tick mark here. 7 pi over, this is 6 pi over 6. One more small angle away is 1 more pi over 6, so that's 7 pi over 6. And my value there is 0.6. So I'm about here. And then when x is when theta is 5 pi over 4, that's this angle here, I'm going to be at 1. So I'll have a point here. And then at 4 pi over 3, I'll be at 1.73. 1.73, not quite 2. Okay. And if I were to do another 5 pi over 4, the equivalent of 5 pi over 4 over here is 17 pi over 12. I'd get another point way up here. So it turns out that tangent, at least in these positive quadrants, appears to be following the same pattern over and over again. Notice that, if I'll connect the dots down here as well. Notice that I have dotted lines every pi over 2, but this one is not an asymptote. Okay, it's not an asymptote at pi. Tangent actually has a value at pi. All right, I think I've probably bored you enough, so I'm not going, and also I'm running out of room. I'm not going to do quadrant 4 in a table like this, but I will make the observation that once I get to my boundary, I can start repeating my values again, root 3 and then 1 and then 1 over root 3. But because I'm in quadrant 4, now only cosine and secant are positive. Tangent must be negative again. So I have like a copy of this quadrant over here in quadrant 4. So I'll just plot those. I'm going to have, for my next 1, 2, 3 tick marks, I'm going to have a height of negative root 3, which turned out to be negative 1 3/4. It looks like it's about there. And then a height of negative 1, and then a height of negative 0.6, and then a height of 0, and I get something that looks like this. I'm not doing a very good job on this one, but I hope that you can see that what's happening is that the pattern is repeating. And in fact, and I'm going to do a very coarse job now, the pattern does in fact repeat forever. So the next one looks like that. The next quadrant would look like that. And the next again quadrant, let's see, I need to make sure I have about the same amount of space. I've kind of messed that up. I made it a little too wide. Let's put some tick marks in here. Quadrants appear to go to about there. Quadrants look like they're about that wide for the most part. And so for every other quadrant, notice that this goes through the x-axis at pi. So it kind of takes up 2 quadrants here. So I'm going to switch to a different color because we're not actually plotting the points for this one. But this graph here, this piece of the graph here is just the beginning of what will end up looking like this. And then the next one will look like this. And the next one, and so on. So tangent repeats in the same way as sine and cosine, but obviously not with the same kind of values. I can do the same thing on the negative x-axis. This will be an asymptote. Halfway through, there's another beginning of a quadrant, right about there, I'll say. I keep changing pen colors here, which is taking me some time. And I'm taking up 2 quadrants here. So this is going to look like this. So the thing to notice here now is I'm going to go in and highlight my quadrant 4 in pink, as I said I was going to call it pink, so we can have all 4 quadrants there. Notice that a tangent, one curve of tangent, one sort of, well, one period, right, takes up 2 quadrants. And if you go back to this first one here, you have to go back into the negative x-axis in order to get a full cycle. So we tend to think of tangent as being one period of tangent as being between negative pi over 2 and positive pi over 2. That's not the whole graph. The whole graph goes on forever, just like sine and cosine did. But one period crosses 2 quadrants, right? We went from quadrant, let's see, we'll look at this cycle here. We went from quadrant 2 to quadrant 3, so between quadrant 2 and quadrant 3. But conventionally, we look at this sort of primary cycle of tangent. It's centered at the origin. It's very convenient and easy to work with. And so we call that, I'll highlight this as though it were a quadrant 4, because it is kind of a quadrant 4. It's the one right before quadrant 1. And if you're on the unit circle, quadrant 4 comes right before quadrant 1. And then I can say, let's see, what should I use here? I guess I'll just use white, a white highlighter. That doubles over my white highlighting in the drawing. Anyway, there you go. So this quadrant 4 to quadrant 1 is what we think of as the first sort of primary, stereotypical almost, if you will, cycle of a tangent. We've talked about the periods before. Sine and cosine have periods of 2 pi. Tangent has a period of pi. Between here and here, negative pi over 2 up to pi over 2, that has a stretch over a stretch of pi units. You could also say, for example, that if we start here and go on until we get back to our starting place, that is one period. Because there's a break in it, we tend not to use that, but that's another way to look at it. Tangent has a period of pi, right? I could think of this as the range of values in the x direction or the theta direction from 0 to pi as covering all the values that tangent will cover once. All right, I'm not really sure where to go with this next. I mean, the next thing we want to talk about is cotangent, but I want to make sure we understand tangent pretty well before we do. This is really not a very good graph of tangent. I think I did a pretty good job on this first quadrant and the second and third quadrants, and the fourth quadrant's not too bad, but then I got lazy and sloppy. So that's not good practice. Most of the time you'll probably be looking at these on a graphing calculator, but as you get to know them, you're going to be working with graphing some of them by hand as well. So just be aware of how you can do that and some of the shortcuts that you can take, because that saved us a lot of time. All right, let's take a look at cotangent next and see how it's related to tangent, at least graphically. Okay, in this video, we're going to be talking about cotangent. And the way to think about cotangent, at least one way to think about it, is to remember that the cotangent of an angle is equal to 1 over the tangent. Now, what I've got graphed here is tangent. This is what we graphed on the previous screen. We have 0, 0. This is roughly pi over 6, comma 0.58. This is roughly pi over 4. Where am I? Roughly pi over 4, comma 1. Nearly pi over 3, comma 1.73. And then I could add a vertical asymptote at pi over 2, which is about 1.57. So let's see, about there. I'm having to use a straight edge on a dynamic screen, and it's not really very happy with me. So I can put an asymptote in there, and I can put an asymptote in, it looks like at about 1.6. I could put an asymptote in here. Push the wrong button. Okay, not the greatest job I've ever done, but you get the idea. At least I hope you do. So this is my central primary cycle of tangent, right? We have 0, 0. pi over 6, 0.58, 0.6, pi over 4, 1. That looks a little high, actually. Pi over 3, 1.73, and so on. And at pi over 2, we have an asymptote. And then we start all over again, but we're in the negative. Now, if I want to graph the cotangent of x, if this is the tangent of x and this is the cotangent is equal to 1 over the tangent, then one way to do that would be to take 1 over each of the values you see here. So let's just stick with this primary central angle, the central period, central cycle for the moment. Here I'm at pi over 6, and my actual value there is 0.58 is 1 over the square root of 3. So let me put 1 over the square root of 3 into my calculator, and I get 0.577 or 0.58, which is about 0.6. And that is actually the value for tangent at pi over 3. So if I go out here to pi over 3, right, pi is 3.14, so pi over 3 is just a tiny little bit more than 1. Then the graph at pi over 6 is going to have the same value as the graph for tangent at pi over 3. Let me see if I can think of a slightly different way to explain this. If I'm going to use a specific angle here now rather than just the cotangent of x. I'm going to say the cotangent of pi over 6 is equal to 1 over the tangent of pi over 6. The cotangent of pi over 4 is equal to 1 over the tangent of pi over 4. And the cotangent of pi over 3 is equal to 1 over the tangent of pi over 3. Okay, now I'm going to cheat because I know that the tangent of pi over 6 is 1 over the square root of 3. That means, give myself a little bit more room here. That means that the cotangent of pi over 6 is 1 over the square root of 3, and that's just the square root of 3. And I found that value earlier too. The square root of 3 is about 1.73. So when I'm at pi over 6, which is roughly here, let me put a tick mark in there so we can see it. Pi over 6 is close to a half. Let's call it there. When I'm at pi over 6, tangent is 1 over root 3. But cotangent is 1 over that, which is, what did we say? 1.73. In other words, pi over 6, cotangent pi over 6 has the same height as tangents pi over 3. All right, now let's do the cotangent of pi over 4. The cotangent of pi over 4 is 1 over the tangent of pi over 4. Well, the tangent of pi over 4 is 1. So cotangent of pi over 4 is 1 over 1, which is 1. So I'm going to have a point there. And then the cotangent of pi over 3 is equal to 1 over the tangent of pi over 3. We know the tangent of pi over 3 is the square root of 3. So the cotangent of pi over 3 is 1 over the square root of 3, which we know to be about 5.58. So that's going to have the same height at pi over 3 as tangent did at pi over 6. Now, this is where it gets interesting, because in this case, it looks like my graph is coming down from potentially an asymptote. We'll need to double check that, and might have to go through the x-axis at pi. Well, we have to use a little bit of hand waving here. You will learn more about this in calculus, but we're going to say for now that 1 over infinity is approximately 0, and 1 over 0 is approximately infinity. Now, this is cheating. This is not real math. Let me tell you what I mean. You can't divide by 0, right? So this is actually undefined. But what if I had a really, 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 really small number here? So small that it was almost 0. And what if we said that instead of infinity here, we had a number that was really, really big, like 1,000 million. Some places they call that a billion. Let's make it a million million. That's a really big number. Well, 1 over a really big number is super small. So 1 over infinity, or 1 over a very, very large number, is close to 0. And the opposite is true here. If I just had 0.1, that would be 1/10. 1 divided by 1 over 10 is 10. If I had 0.01, that would be 1/100th. 1 divided by 1 over 100 is 100. 1 divided by 1 over 1 million, 1 over 1 million down here, 1 divided by 1 over 1 million is a million. So the smaller this number gets, the bigger the whole fraction gets. So if this is 1 over 0, or approaching 1 over 0, we can say that that's approximately infinity. Now, infinity is not a number, it's an idea. So this is really not good mathematics, but I'm hoping it'll be enough for you to understand what's going to happen in the next part of this video. And that is this. If I'm going to take this value, divide 1 by this value, and get this value out, then what happens when I take this value and divide 1 by this value, this y value? What's going to come out? Well, this is 1 divided by 0. And it's not infinity, but it approaches infinity. It's asymptotic. And what happens when I take this infinity, which isn't really infinity, but it's approaching infinity? It's almost infinity, right? It's really, really big. The higher you go, the bigger the number gets. 1 divided by that is close to 0. So that goes through 0. And then the same thing happens in reverse on the opposite sides, where I did have a point down here for tangent. It's going to be up here on the same height as this one here for cotangent, where I had a height of whatever this is for tangent. It's going to be down here for cotangent. And then it's going to go through this one. So I'm kind of trying to visually line these up. I'll have the same thing here, and so on. And actually, the only ones I really want to do are this one here, and maybe, let's see, where am I going to go through? My asymptote here is between this number here and this number here. Remember from our tangent graph that we found that there was an asymptote at 3 pi over 2? Well, 3 pi over 2 is about 4.7, so we're about there. About there. So I'm going to come through the x-axis there, and then I'm going to have a similar arrangement of points down here. That one's a little off. There we go. Okay. And now I'm going to do the same thing over here in this quadrant before quadrant 1. And I'm actually just going to go ahead and plot a bunch of those points. I missed one. Let's put that in. I'll also point out that where I used to have an infinity, where I used to have an asymptote, that's the asymptote for tangent, I'm going to have a 0 for cotangent. And where I used to have a 0 for tangent, that's going to be a new asymptote. So I'm going to have an asymptote here, and I'm going to have an asymptote for cotangent here, but where I did have an asymptote, I'm now going to have a 0. So this graph looks something like this. And that pattern repeats. It goes on and on and on forever. I've given you 3 cycles here, but the main reason for that is to make this observation. In the case of the blue graph, which is the tangent graph, we said that the period we were going to call our primary period was 0 to pi over 2. The graph that I found here to use for this purpose was labeled in integers rather than in radians, unfortunately. But recall that pi is approximately 3.14. Call it 3 for now, and you'll see that half of that, or pi over 2, is about 1.5. It's a little bit more than 1.5. So this is actually pi over 2. And that's an asymptote for my tangent graph. but it's a 0 for my cotangent graph. So for my cotangent graph, I have to find another single whole stretch of a graph that takes up one cycle, and I'm going to call that 0 to pi. See if I can do this without my asymptote in place. That's not too bad. So the yellow highlighted region is the region that we think of as the primary region for tangent. And the pink highlighted region is the region we think of as the primary region for cotangent. They are not the same. So we say that they both have a period of pi, right? This goes from 0 to pi, and this goes from negative half of pi to positive half of pi. So that's also pi. They both have periods of pi, but the period is whether you start at a 0 and then go on for your, I'm tracing tangent here, starting at 0 and going up first and then coming up from the bottom and coming back to 0. That's one period of tangent, the blue graph. But it's split in half here. It's weirdly dysfunctional. So we go back and take this whole cycle instead, right? So that's still a period of pi, but it covers negative pi over 2 to pi over 2. And then for cotangent, notice first of all that it's kind of upside down, but it's also shifted over. And for that one, we say the period is pi, but we're gonna look at it from 0 to pi so that we have a whole section, a whole unbroken section. All right, I have one more observation to make on this slide, and that is this. The tangent of an angle plus any multiple of pi, we'll call that k times pi, is equal to the tangent of the original angle. What that means is if you pick a value of x, let's call it 1, why not? And find out what the value of tangent is there. Looks like it's about 1.5, a little less than 1.5, maybe 1.4. Then if I add pi to this value of x, instead of 3.14, I'm going to have 4.14, go up to the value for tangent, and I'm going to get the same thing, just a little more. I can't remember where I was on here. It's almost this point here, right? It's almost this point here, and a little over 4.114 it almost gives me that same point there. So, and I can do that for any multiple of pi. This was 1 plus 3.14 plus 3.14 more, or 1 minus 3.14 minus 1, 2, 3.14 gives me the same value again. Okay, so that's another way of saying that tangent cycles through every pi units. Okay, and the same is true of cotangent. I won't illustrate that because you can do that yourself. Take any multiple of pi and add it to your angle. You'll get the same cotangent value as you would for the original angle. Okay, on the previous screen, we graphed tangent. On this screen, we graphed cotangent. On the next screen, and I can't quite decide whether it's going to take me 1 or 2, but on the next screen, we're going to graph cosecant and then secant. And the reason I'm going to graph cosecant first is because cosecant is 1 over sine, and we're a little bit more familiar with sine than we are with cosine. They're both fairly equivalent in our minds at this point, I think, but sine is the thing we learned to graph first. It's the thing we met first when we were learning about the trigonometry of right triangles. So we're going to deal with its reciprocal first. I hope you recognize this as the graph of y. I'm going to do this in blue because I want it to match the graph itself. Y equals the sine of x. Okay, again, we're using integers here instead of radians. Well, it's in radians, but we're using integers instead of multiples of pi. So that makes things a little bit awkward. But I've taken the liberty of plotting some of the points on the graph. This is just a Google search for y equals sine of x, or graph of sine, and it just spits out this graph. And I've just screen captured that. So I know some of the points, some of the values for sine are 0, 0, pi over 6, 1 half, pi over 4, square root of 2 over 2, pi over 3, square root of 3 over 2, pi over 2 is 1, The sine of the square root of, sorry, the sine of pi over 2 is 1. The sine of, so what's the next one? Pi over 2 plus pi over 6 is 3. 4 pi over 6, which is 2 pi over 3. So 2 pi over 3, the sine there is the square root of 3 over 2, and so on. Now, again, I'd like us to remember that the cosecant of x is equal to 1 over the sine of x. So I'm going to take each of these black dots and find the value 1 over that number, and then I'm going to plot those points in some other color. I haven't decided what yet, maybe pink. So first I'm going to go figure out what these values are, and I'm going to write them down for, I think I'll do them for this quadrant here and this quadrant here. That's not a quadrant, that's 2 quadrants. And this is 2 quadrants. So I'll do it for those 2 quadrants, and then I'll come back and we'll talk about what to do with those values. So here we go. We know 0, the height of 0 is, that's pretty obvious to spot, right? Easy to spot. 0.5, that one's easy. That was the square root, sorry, that was the sine of pi over 6 is a half, and it's on the graph here, it's given as a decimal instead of a fraction. The square root of 2 over 2 is about 0.7, and the square root of 3 over 2 is about 0.87, or we're going to call it 0.9. And then at pi over 2, the sine is 1. And the same is true in quadrant 4, or the quadrant negative 1, I guess you could call it, right? It's the quadrant before quadrant 1. The values are the same, but they're negative, okay? And then these values will also be the same over here, and these values will also be the same over here. I'm trying not to clutter up the graph too much. Now, again, we can say that the cosecant of, let's just go with pi over 6, which is equal to 1 over the sine of pi over 6, but we know the sine of pi over 6, it's 1/2. So the cosecant is 2. Now, unfortunately, my graph doesn't go high enough or low enough for me to be able to graph that one. But suffice it to say that at pi over 6, when x is pi over 6, right about here, I'll put that in as a pink tick mark, my cosecant value is going to be way up there somewhere. And at negative pi over 6, it's going to be way down there somewhere. All right, that's pi over 6. Let's do pi over 4. So I'll take the pi over 4s out of there, take that value, sorry, the pi over 6s. We'll stick pi over 4 in there instead. It's the right pen. We know the sine of pi over 4, it's the square root of 2 over 2. So the cosecant of pi over 4 is going to be 1 over the square root of 2 over 2, which is 2 over the square root of 2. And as a decimal, that's about 1.4. So where the sine is 0.7, the cosecant is going to be 1.4. So I'll put that in, let's see, 2, 4, it's about there. About there. I'm trying to line it up with the right value in the x direction as well. I think it's about there. I need to move that over just a little bit. There we go. Remember that the point for cosecant above this one, or that lines up with this one, is way up there at 2. This one is, oh gosh, it's above this point here, but it's up at about 1.4, so it's maybe about there. And then the next one is pi over 3. At pi over 3, sine is the square root of 3 over 2. So let's get those out of there. And let's talk about the sine. The cosecant of pi over 3 is 1 over the sine of pi over 3. The sine of pi over 3 is the square root of 3 over 2. And the cosecant, therefore, is 1 over the square root of 3 over 2, which means the cosecant is 2 over the square root of 3. And that is approximately 2 over the square root of 3 is about 1.15. 1.154. So it's just over 1. So at pi over 3. Pi is about, well, pi is exactly where you see the 0 there. That's pi. And a third of that, a third of 3 is 1, so it's just a tiny little bit over 1. Up above that is, for cosecant, is 1.15. It's about there. Okay, maybe that's just a little bit too low. There. Now, the next one is pi over 2. The next angle is pi over 2. Halfway between these two is pi over 2, and its value is 1. If I stick a pi over 2 in here and here, I get a 1 over 1, because the sine of pi over 2 is 1. 1 over 1? Well, that's just 1. Now, the same thing is going to happen on the other side, because I'm going to have 1 over this value gives me that height, 1 over this height gives me that one, 1 over 1, and so on. So over that point, I can put a point that's the same height as the one I did earlier. And I can do the same thing down here. 1 point just over 1 there, and then 1 point, I can't remember what we came up with, 1.4. So over this point, I have 1.4, and I have a matching point over here. Now, if I connect the dots here, I get something that looks like this. And again, I'm drawing these by hand. I'm not doing a terrific job, but I hope you get the idea that this weird sort of one loop here, if you will, and one loop down here, this is the graph of cosecant. It's not the whole graph, of course, because like all the other trigonometric functions, it goes on in both directions forever. But there are some observations that we should make about this graph as well. One is that where there's a 0 for sine, I now have for cosecant 1 over 0, which of course isn't really 1 over 0, but what we say there is that there's an asymptote, right? 1 over 0 means we're getting closer and closer and closer to 0 for the denominator of a fraction, and therefore the actual value we're looking at is an asymptote. And let's see, I'll put one more in here. There is an asymptote at every single value, every single time sine has a 0, has an x-intercept, cosecant has an asymptote. In the same way that wherever tangent had an x-intercept, well, that's not quite true, not for tangent, but in this case it is. Every single 0 of sine becomes an asymptote for cosecant. Now, if I could take away this this background graph, which I'm going to try here in a second. I'm going to take away the background graph, the blue graph, all the black dots, and all the asymptotes. Well, I don't know the asymptotes. Maybe I'll try to leave them there. You'll see what's left in pink is the graph of cosecant. Okay, I think I more or less managed that here, although my asymptotes went missing because they were black dotted lines, and now I have a black background, so the black dotted lines are not showing anymore. So I'll just put them back in very roughly. I'll fix my curve here. And I'll make the point that this is necessarily sort of truncated, but in fact, these actually go down forever, and these ones go up forever. All right, just there's a limited amount of space on the screen here, and so it's there was even more limited space in the version that I had up a minute ago, because it was on this white field that ended before the bottom of the screen, right? The white field sort of ended up here, so there was nowhere to draw. Anyway, this is what the graph of cosecant looks like, and I'll make some more observations. These are at 1. These have a height of 1, so if I have an x-axis or a y-axis in here, which would be right here, That's my y-axis, and I can put an x-axis in here. I think I'll try that again. That's a little better. Then I can make these observations. One is that this is -1 and this is +1. And another is that a single cycle of cosecant is more than just this loop right here, right? This doesn't repeat starting here. It goes all the way over here before it starts to repeat. So I might put one more asymptote in here, and then we have to figure out how wide is this region here, because we need all of this region to figure out what one cycle of cosecant is, because we need one of the right side up loops and one of the upside down loops to make a full cycle. This time we can't get away from the fact that there's an asymptote in it. So we'll just take the cycle that starts at 0. If I started back here, then I'd have an upside down loop and a right side up loop. I'd have one of each, but there's a break in it. So if I start at 0, I have a right side up loop and an upside down loop, but there's a break in it. So there's no benefit to using one over the other, except that this time, if we start at 0 instead of starting back here, if we start at 0, then our whole domain, our whole period is all together in one positive, it's all on the positive x-axis, right? So we're going to go ahead and say, for the sake of convention, that a cycle starts at 0 and ends over here. Now, where is over here? Let me go grab another pen. And let's remind ourselves where this graph came from. If I ask you if this is the graph of cosecant or of something else, one way to test it is to say, well, if it's cosecant, then all the graphs, all the points that I have here are 1 over something. 1 divided by something larger than 1 is going to be smaller than 1. So this graph must have come from something that looks like this. I'm not doing a very good job here. And that looks an awful lot like a sine. Because of my scale, I know this is 1 and -1, so this is a stretched sine, but it's a sine nonetheless. And I could keep going here, right? I could go down here, I could put another one in here. And everywhere I have a 1 for the pink graph, that necessarily came from a 1 over 1 for the graph that it was derived from. Anytime I have a 1, I have a 1. But every time I have something larger than 1 on my pink graph, I must have something smaller than 1 on my white graph. So this pink graph, because of where the white graph starts, must have had to come from sine. And because cosecant is 1 over sine, and sine is 1 over cosecant, the sine graph produces the cosecant graph when you invert or reciprocate those values. So this pink graph is what the graph of the cosecant looks like. Now let's talk about the secant graph. Okay, we're pretty experienced now at graphing these things based on the graph of the reciprocal. So I'm going to start by making the observation that the secant of x is 1 over the cosine of x. And that means that I can take the values in this graph, for example, let's start with a half. And when at this value of x, when I flip over 1 over 2, I get 2. And so once again, my value for this graph, for this value here, is way off the charts. I can't quite graph that, but I can graph 1 over this one, 1 over this one, and 1 over 1 is 1 again. So in the same way as I had a graph for cosecant that came from finding the reciprocals of the values, the y values for sine, the graph for secant comes from finding the reciprocals of the values for cosine. So this graph looks something like this. And I really should extend this in the way that I tried to for cosecant. I didn't do a very good job there. So cosecant and secant look very similar, and that's not a coincidence because sine and cosine are very closely related. In fact, if you'll recall, cosine is just a shift, a horizontal shift of pi over 2 for sine. So if I add to this graph a graph of the sine, and I'll just do it by hand. I'm using blue because I want it to have the same look as the graph for cosine, although I doubt very much that you will mistake my handiwork for for the computer generated graph here. That's actually not too bad. There is one cycle of sine, okay, and 6.28 is 2 pi, so that's just about right. And it's just a shift over, and you'll notice that wherever there was a 0 for cosine, there's a high point for sine. Wherever there's a high point for cosine, there's a 0 for sine. They're just shifted over. Now, that's cosine, sorry, that's sine, and 1 over sine looks like this. So cosecant is actually a shift, or secant, I should say, is just a shift of cosecant. So sine and cosine are related as a shift of pi over 2, and sine and cosine and secant and cosecant are related in the same way. That is a shift of pi over 2 from one to the other. Now, I think what I'll do is get rid of my sine graph at this point, because I don't want it to confuse things too much. And just make one other observation here. This one doesn't need to be too long. And that is that I can tell that my pink graph here came from cosine and is therefore the graph of secant and not cosecant because of where it starts. If I again remove the white background here and the graph that goes with it and stick an x and y axes in here, I'm having trouble with my axis. It's hard to draw by hand, straight lines. This is x and this is y. Then you can see the pink graph comes down to its lowest point, which is 1. That's still at 1. That comes down to its lowest point over 0, over x equals 0. Whereas this other one, the dotted line graph here, comes down to its lowest point here, which turns out to be pi over 2. Let me put in a couple more marks here. This would be pi, 3 pi over 2, and 2 pi. And cosine does this. It starts at 1, goes through the x-axis at pi over 2, it goes down to negative 1, goes through the x-axis at 3 pi over 2, and it's 1 again at 2 pi. So that's my cosine graph. The pink graph is the reciprocal of that graph, right? And so therefore it's the secant graph. Whereas the graph of cosecant, which is this dotted line here, comes up to 1 here, and it goes to 0. It goes to 0 here at x equals 0 because the dotted line graph is going to infinity. 1 over infinity is 0. So this graph looks more like, let's see, it's going to come to about there, right? So my dotted line has to be cosecant because it comes from 1 over sine. You can match them up, right? This cup to this cap. Here, my white graph is starting here is cosine, which means this solid pink graph has to be secant because they line up, right? They have that relationship that 1 over 1 is 1. The pink graph is 1 over the white graph. All right, let's get rid of all the extraneous stuff, and let's just take a look then at secant, the graph of secant. Now, there are more of these loops over here and down here. They go on forever. But again, my period is 2 pi, and it doesn't matter whether I start at 0, 1 or at negative pi over 2, well, basically infinity. It's going to take me 2 pi. It's going to take me a distance or a window of 2 pi in the x direction to get back to where I started. So starting here at 0, 1, my secant graph goes up, then comes up from the bottom, hits a maximum locally of -1 and goes back down. Then it comes down from the top and it finally gets back to +1 way over here at pi over 2. So in this case, I have two asymptotes, two breaks in the graph, where I would have had two zeros in my graph of cosine. If I'd started back here, then I would have had the same asymptote here, but I'd have another asymptote here, and I would only have gone to, this is, let's see, negative pi over 2. I'd have to go from negative pi over 2 to 3 pi over 2. Let me highlight that. It's very weird. This is negative pi over 2, and I'd be going to 3 pi over 2, that window there. And that, it's just uneven. It's not symmetrical, right? So it's easier to work with a graph. It's easier to work with a function. If you think about a single period, on one hand, you get a nice whole loop here and a nice whole loop here. But your period, although it's still a 2 pi long period, it starts at negative pi over 2 and ends at positive 3 pi over 2. It's not symmetrical. So for that reason, one convention anyway, is to start at 0 and go to 2 pi. Yes, you have half loops in your single cycle, but you have a nicer window of values here, a nicer range of values to work with. There is another school of thought that says that doesn't matter. We should go ahead and start where we have as few breaks in our graph as possible. So we have a whole right side up loop and a whole upside down loop. And who cares if our range of values is asymmetrical? But our textbook, and I have to say I tend to agree with them, working with the domain values is going to become very important fairly soon. And I think it's easier if you can work with domain values that are all positive and symmetrical. So we're going to stick with that. I haven't spent a lot of time on secant because it basically is just a shift of cosecant, as we talked about earlier, in the same way as cosine is a shift of sine. Well, that pretty much does it for these other four graphs. Tangent and cotangent are related to each other. Secant and cosecant are shifts of one another in the same way that sine and cosine are shifts of one another. Secant is related to cosine, and cosecant is related to sine. In the next video, we're going to be looking at transforming these graphs, specifically the tangent and cotangent graphs in the next video, and the secant and cosecant graphs in the video after that.